But we still use the
I
word.
thought you'd have a chance to pick out the good parts and dump the bad ones.
Oh, no, no.
It's all good.
It's
all
all
good.
Oh, this is going to be live?
It's live right now.
That's different.
It's not a problem.
Challenge, yeah.
No, it's no challenge.
They'll take care of us.
Well,
we'll be
we'll
just
see.
fine.
Yeah.
You were live back there when we were talking. You're live here now. It's the same thing.
Okay.
Absolutely.
It'll be good.
At least it'll be a new experience for
Yeah.
me.
There you go.
I've never done this either. Although John did my very first interview ever on camera. The very first, when I was at Detroit Diesel, many years ago.
Oh, yeah,
You remember that? We were
Oh, you're
standing
there.
outside the
Right.
pilot center there.
Yeah.
Yeah, that was the very first camera interview I ever did.
Unbelievable.
Yeah.
Have you gone by that place recently?
No, I haven't. Have you been there?
It's amazing.
I mean, it's gorgeous. I mean,
Wow.
boy, they spend a lot of money. I mean, on Telegraph when
Yeah.
you go by, you wouldn't know it's the same place. I grew up around there.
Yeah.
So.
It looks very modern.
Does it?
Very modern.
Yeah, Mercedes spent a lot of dough.
Yeah,
Right.
I'll have to drive by there sometime.
Yeah.
I understand a lot of the people I worked with have retired or moved, different jobs, different places. So
Sure.
yeah, I don't get over there.
Right.
So
And they're rebranding it. They're trying not to call it Detroit Diesel. They're just calling it Detroit.
Right.
I saw that. I still have, it doesn't roll off the tongue.
No.
Right. Well, they try to use and so there's like the Detroit transmission that they have for the trucks, and I mean, so
Yeah.
everything is Detroit to, I
Yeah.
think, indicate it's more robust and
Right.
Local.
than the other guys.
Yeah.
Well, not just local. I mean, Daimler, German company, but there's this panache with Detroit to what Gary is saying. Strong, powerful, real working
Right.
stuff.
Yeah,
Yeah. Interesting.
because you can buy a normal transmission or a Detroit transmission.
I see. Got it.
We're ready? Okay, yeah. Okay, we want to thank everybody who's already tuned in live. We got a great show coming up. It's going to be on literally the history of the fuel cell, the automotive fuel cell. And we've got Floyd Wyczalek. Did I say that right, Floyd?
You did?
All right. Who worked on the original GM Electrovan. Electrovan was the name, right?
That is. Yep.
So if you got questions about it, shoot us an email. Send it to viewermail@autoline.tv, or we'll take a phone call too, and that number is 620-288-6546, and we'll get going here in just a moment. Watch Autoline After Hours live at Autoline.tv every Thursday at 3 p.m. Eastern Time. That's 12 p.m. Pacific. You can subscribe to this podcast for free by searching for Autoline in iTunes, Stitcher, or YouTube.
Autoline After Hours is brought to you by Bridgestone Tires, your journey, our passion, and by Lear, a global leader in automotive seating and electrical systems.
Well, welcome everybody to another episode of After Hours. And Gary, great to be back in the studio with you.
Absolutely, yeah. How you been?
I've been doing great. You were out where? Hawaii last
I
week.
was in Hawaii.
You dog.
Yeah. So it's a long way to go. I mean, it's a long way to go.
But worth it, right?
Yeah.
Worth it.
Well, we went to drive a car, so.
Yeah.
That was the Honda Odyssey
Right,
minivan
right,
launch.
yeah.
So, now, well, maybe we'll get into that. But what we really want to talk about on this show is the history of the fuel cell used in automotive. And the reason we're doing that is we have Floyd Wyczalek, former General Motors engineer who worked on the original General Motors Electrovan, which was powered by a fuel cell. And Floyd, welcome to Autoline After Hours.
Well, thank you.
We got Charlie.
And we have Charlie Freese, who's the executive director of all fuel cell development, or all fuel cell activities, I should say, at General Motors. And Charlie, it's great to have you on this show.
Thank you. Great to be here.
We've had you on the TV show. Now we get to have you on After Hours. So
Great.
So
good to
these
have
two
you.
guys are the entire history of fuel cell technology, I think, because yours was the very first automotive fuel cell, right?
Oh, yes, this is the very first.
Floyd, how did that start? I mean, what launched a project at General Motors to do a van or any vehicle powered by a fuel cell?
Well, the way it turned out, General Motors senior management adopted a policy of zero-emission vehicles in the 60s. And engineering staff division at the Tech Center proposed in response to that a two-step program, a battery electric Electrovan, and to be followed by a Electrovan fuel cell powered vehicle. The Electrovan's purpose was to develop independently the traction motor, make it compact enough to put in a car, and an infinitely variable control system, which just did not exist at that time. Then once that was done, that would be transferred into this Electrovan, and we could concentrate on the fuel cells. But the fuel cells at that time were a spin-off from the Saturn Apollo program. And the reason the Saturn Apollo program had fuel cells is because they had hydrogen and oxygen available, and they needed both water, drinking water, and electricity in order to make the round trip to the moon. Silver zinc batteries, which were the best available at that time, just weren't good enough for that kind of a lengthy trip. So what we did was to visit Pratt & Whitney, which was producing a serial, had a production line going on a serial group of fuel cells for the Apollo. That was a single cell, a single module consisting of 31 cells, 31 volts, and the entire system for the Apollo had a mass of about 91 kilograms, and that's about 200 pounds. And so we got together with Union Carbide and asked them to, in a joint venture, to reduce that to practice. And what they did, they took that Apollo fuel cell and made it the size of a lead-acid battery, which was available so that we could put that in a van. We then ended up with 32 of these, which covered the entire bottom of the of the van, of a GM handy van. And it turned out that the handy van turned out to be the fuel cell itself. It was that big and that heavy. So our first challenge at the time was to develop a fuel cell testing laboratory. They just didn't exist. We had to imagine this. And the next thing we had to do was the Electrovan. And we brought in a team of consultants called PERT planning, in which you were able to develop a PERT plan in order to identify the critical path, because the assignment, Ed Cole, who was executive vice president at that time, he was an innovator like Dan Nicholson, the current vice president of Global Power Systems. They were two identical people, 50 years apart. And they thought and acted the same way. And so he pursued this, and we continued to do that. So with the PERT plan, we had a 10-month window in which to build the Electrovan and get it operational for an international press conference at the Tech Center. And all we had to do, our mission was to drive by once all of the reporters and all the executive vice presidents of General Motors in front of the styling dome. So we set out to do that. But in order to do that with people who had never heard of a fuel cell, the first thing we did was fly down to Cleveland, the Parma Union Carbide Research Lab, and have them give us a one-day crash course on what is a fuel cell. Hardly any, 99% of the people we took with us down there hadn't even heard of it. The only people who knew about that were an engineer or two, and Craig Marks, who was the equivalent of Charlie Freese. He was the executive director of advanced power plants at that time.
So wait a minute. You had a crash course
One
and
day.
10 months to come up with a moving vehicle.
That's right. That was
Charlie, could you do that today?
Oh, well, probably not starting with where they did. But, you know, there are a lot of things about what Floyd described there, just getting a team together, very focused on one thing, and then quickly trying to implement something with a clear set of objectives. And the team has done some things like that with all the head start that came out of the Electrovan program and all the work that's come in since then with that ZH2. We did that in 9 months. From when we started to kick that vehicle off. We had a lot of different things happening. We were already evaluating vehicles like that, but when we finally decided we wanted to build one and demonstrate one for the U.S. Army, that was about a 9-month program.
So this is a hydrogen-powered pickup truck.
It is, yeah. It's the Colorado is the base architecture for it. So the Chevrolet Colorado ZR2, which is the off-road capable system, what we did was we coupled that with the fuel cell, which it's an interesting thing when you start talking about electric drive and the very broad torque range that you get for that over high torque over a wide speed range. You can basically apply that to an off-road vehicle and make that vehicle do things that wouldn't be possible with any other propulsion system.
So Floyd said that the entire Electrovan was filled with the fuel cell. Is the entire bed of the Colorado filled with the fuel cell?
No, but so that's part of the progress. But the same way that with Floyd's team that they were so constrained over packaging the fuel cell and all the things that make the fuel cell work in the vehicle, the hydrogen storage and the way that we've developed fuel cells over the years have similarly continued to be challenged by that, and we keep working on that. That's where the development has been focused. So actually, one of the biggest fleets that we've ever put together and demonstrated a lot of mileage with has been the Equinox. That was the Project Driveway fleet. And one of the reasons we picked a vehicle as big as the Equinox was that we could put the fuel cell system in there and package it in that vehicle. So that was part of the driver for it. And then getting 3 tanks of hydrogen into the back. But since then, the size has come down dramatically. We call that the Gen 0 system. The Gen 1 system was about half the size, half the mass. And then the Gen 2, which is the one that we're commercializing now, that one is maybe about 60% of that size. So it's been a trajectory down to smaller and smaller. So we can get into a low hood line vehicle now, but we're still dealing with hydrogen storage. It's still in a tank that likes to be cylindrical, not something that's easily packaged in a flat floor. So that's one thing that we continue to work on. And then, like Floyd said, the batteries. Batteries are still heavier parts of the system. You like to get them low for center of mass, and we continue to look at ways to optimize battery packaging. So that's something that electric vehicles continue to deal with.
Yeah. Floyd, how did you end up on the program at GM? Why did they select you to be part of it?
Well, Craig Marks, the equivalent of Charlie, appointed 2 people to start the ball rolling. Myself as the project manager of fuel cell development, and Ed Rishavy was to do the Electrovan. Now, the PERT plan said that we had to do both in parallel at the same time. We couldn't do them in series in 10 months. So both of the projects started at the same time. Ed Rishavy stripped a handy van, and we went into an empty test cell and appointed a team of technicians and engineers, and one of the engineers that I appointed was Dan Frank. He was an electrical engineer, and he was to be the hands-on fuel cell simulator development guy. And in order to get that team rolling, we had to use what we call brainstorming, because no one could have possibly imagined what a fuel cell test cell would look like. So we had to involve the entire team so we would get ideas from the bottom up. And brainstorming in those days consisted of myself on Monday writing on a whiteboard the ideas that came forward. And the general rule of brainstorming is that you can't criticize any idea, no matter how dumb it looks on the whiteboard, because the moment you do that, you shut the process down. So that was the way we got started. But if you finally see what a fuel cell test facility looks like, you wouldn't believe that any one person could ever imagine what that would be like. So that had to involve everybody, and that's how we did that part and got it rolling.
Let me ask you a fundamental question. So this is 1966 that you're doing this work, correct? 1966?
Yes, this is 1966.
Okay, so NASA's using the fuel cell to provide power for the capsule, the lunar capsule, correct? Not to make it go up in space or
Oh, no,
not for a lunar...
well, in order to, in order to have a computer running in the lander and to operate all the controls, that had to be computer controlled. The early digital computer at that time had 32 KB of memory. And so you also had to have life support in the lander, and for 3 days, and you had to supply 2 human beings with all of the things that a human being needs to do. He's got to eat something, he's got to drink something, and he's got to have controls, and he's got to be able to communicate with Houston. So that's the purpose of the electrical. It's a very high energy consumption requirement for those launch vehicles.
In that application, it was basically a stationary power supply. I mean, I know that it went up in space, but it was basically stationary. How did you guys think we can make a car go using this energy?
Well, Pratt & Whitney worked out a system in which they had 3 of these modules in the service module. Beneath the lander, there's a service module that provides all the amenities that are needed: water, hydrogen, oxygen, atmospheric control within the space capsule, and dehumidification. All of those things were a tremendous energy consumer. So they had to have fuel cells. And if they didn't have a fuel cell, they couldn't have, the moon mission would have been impossible.
So you, at General Motors, 1966, you start a program for an electric van and a fuel cell van. How did it go?
Well, we didn't do that at the same time. We started in 1964 on the Electrovan, and Ed Vershavy was the project manager of that. And of course, you can't do anything in General Motors without involving all the divisions. So you drew on the entire corporation in order to do that. We had research laboratories, we had Harrison Radiator, we had Defense Research Laboratory, and all of the talent that we needed was drawn for those 2 projects. Once we developed the Electrovan, then we went on to the fuel cell program.
Okay, so you had 10 months to do that. Did the program go smoothly? Did you have all kinds of problems? How did it go?
Well, in 1964, we did the Electrovan 1, and then the Electrovan 2 was an improved version, and then that is the drive system we transferred into the Electrovan. It's in 1966. So it was 1964 first, 65, and 66. But in 66, to do the van, which we started in 1966, that was a 10-month program. But these 2 programs were 2 years.
Okay.
Those are Corvairs, right?
Yes.
Yeah.
So little cars, the Corvair. So did you think about using the Corvair for the fuel cell vehicle?
No, we use silver zinc batteries.
No, the Corvair car.
Oh, yes, it was the Corvair. Now, the reason that was possible is because Ed Cole, was chief engineer of Chevrolet prior to that at that time, and he is the one that's responsible for the development of the air-cooled engine, rear engine drive Corvair, which was a perfect platform in order to develop a battery electric car.
So Floyd, what were the things that you had to decide when you decided you couldn't make the fuel cell out of the Corvair? You needed to jump to something different, the Electrovan. What made you move to a van instead of the smaller Corvair vehicle?
What made the Electrovan?
What were the decision parameters that pushed the team to use something as big as a van instead of a small?
Well, the reason we were able to consider doing the Electrovan is because we knew the Apollo had fuel cells on it, and we knew that in 1964. And then our initial inspection showed that that was not, that was too bulky and heavy in order to even do an Electrovan. And that's why we got together with a joint program with Union Carbide. And Dr. Charlie Winters was formerly from Oak Ridge and had worked on he was responsible for plutonium for the atomic bomb. So what they were trying to do at Union Carbide was spin off technology from that program and make a commercial product of some kind. So they were very motivated to do this.
Charlie, here you've got a guy who started 50 years ahead of you. How did you two get hooked up? I mean, how did you two get to even know each other?
Well, I asked him the same question. How the hell did you find me?
Well, so when the Electrovan was coming up on its 50th anniversary, and that happened late last year, so we thought we needed to recognize that event because honestly, that blazed the trail for everything that we do in fuel cells now. The reason we believe we can do that all started with that vehicle, so it was an important event. So I asked Joe Mercurio, who was on our team, if he could try to do some research and see who worked on the program and see if he could find some people that had firsthand experience. And he found Floyd was living not too far away, actually, from Pontiac, where our facilities are. So he contacted Floyd, and I'll let Floyd tell that story because he'll tell it better than me.
Well, I'll tell you what happened. I came back from Costco, and on my recording machine, there was a message that said, Floyd, I'd like to talk to you about the 1966 Electrovan. Call this number. It didn't say who it was or what. So I said, geez, I said, that's got to be it can't be real. That's ancient history. So I ignored it. Next day, I got up in the evening, after making supper, went into the office, and there was that recording again. So this time I jumped on Google and did a reverse phone lookup, and it said Joe Mercurio, living about a half a mile away from me in Bloomfield Hills. I said, well, I better call him. But I thought, well, this guy's got to be a student, and he's doing some a doctoral thesis or something on fuel cells. So I called Joe, and he says, GM is celebrating 50 years of fuel cell development. He says, you're it. So he came over on Saturday, and we chatted on my screen porch for about 2 hours like we're doing now. And he says, well, you can walk and talk, so I bet you're invited.
But Floyd's very humble. I mean, we asked him to come to meet our team, and he gave an hour lecture to the fuel cell development team, and it was all the history that we had never even heard about this. I mean, it gets lost so easily. A report is written, but that doesn't really document really how these things happened and those stories behind it. And he had that team mesmerized for an hour, taking notes, and he's come back a number of times to talk with innovators about how to innovate and how he's done it through the years in his job. And there's lessons that all of us can carry forward based on what he drove his team to accomplish with the Electrovan.
Floyd, when you see what Charlie's doing, when you go to Pontiac, do you recognize the technology? Can you
Well,
say, hey, I know what that is?
I'll tell you what happened when after I delivered the lecture, they took me through the fuel cell development laboratory, and I thought I was on the Starship. And I thought this is a teletransport into the future, because I couldn't recognize anything. I said, gee, this looks like a spaceship here, and it's nothing like the crude fuel cell development laboratory we had. It was unbelievable to me, and I still can't believe it to this day. So GM has spent $2.5 billion on building that facility, and their commitment to fuel cells is where they're putting their money where their mouth is, I can tell you that.
Hey, look, we've got to take a quick commercial break right now, but don't go away because we've got a lot more to talk to you about. But right now we're going to give a shout out to Bridgestone, which is a great supporter of shows like this. Okay, we're back. We're talking with Floyd and Charlie all about 50 years of fuel cells. And Floyd, we got a question here from Armand. And Armand wants to know, how safe was the fuel cell that you helped create? Were there any scary moments?
Well, there are always untold stories, but with this particular program, we were what I call risk averse, and that's typical of General Motors. And we took all of the safety precautions that were possible and completed the program without injuring or hurting or anyone at all.
Charlie, you said that Floyd talked to your team and that they were mesmerized about it. What was it? What was it that really captured their attention?
Well, you know, so right back as far as I can remember it, working on GM and fuel cells, every presentation where you're trying to talk about a fuel cell, it always starts with a picture of the Electrovan. It's always there, right? But and you go to the Heritage Center and there's the vehicle. But what was so interesting was to hear the stories about the personalities and how people brought the technology as the very first technology transfer out of the space program. It hadn't really been done before. And we try to do that now in many places, right? You know, there are many things that we deal with every day that came out of things like the space program and the development behind that. But to hear it as it relates to something in the automotive business that we, you know, we're all involved with is very interesting. And then just to hear some of the things like the processes in terms of you know, how you develop the technology around running a pulse width modulated motor, or, you know, things like that. All of these things are things that you can trace these histories back that we're working on now, all the way back to those types of things, and understand many elements all the way back to basically Floyd's team broke that ground, and ways to deal with hydrogen and liquid hydrogen. I mean, that continues to be a process that we continue to evolve, and we continue to develop and find ways to optimize and make it safer, and continue to develop that. But a lot of that all began in this very program because they had to do it for the very first time. So it's really interesting, and the team could really relate to that. So,
Floyd, where did you get the hydrogen?
Where did we get it? Or
Yeah.
Oh, well, at that time, it happened because of President Kennedy's lunar landing challenge, that hydrogen and oxygen became available from Linde and Air Products, which were two separate companies. What we did was install a Linde liquid hydrogen sphere on the Tech Center campus, where there is a parking lot now, but and Air Products oxygen tank right at the end of the dynamometer building, where the fuel cell laboratory was built at the very end of it. And so the most humorous thing that we did at that time was, since we had potassium hydroxide, which is a alkaline solution, circulating through this fuel cell system at 160 degrees, we had everybody wear full clothing, face masks, and brought in at that time, the Tech Center was in farmland, and it happened that there was a farmers co-op just opposite the north end gate. And we brought in a horse trough watering tank, so that if we ever had a spill, they could all just jump in and neutralize that, because we filled it with ophthalmic grade 3% solution, eye wash solution, which is an acid that will, boric acid, which will neutralize the alkali. But we never had to use that. That just gathered dust there right next to the fuel cell.
Charlie, I'm sure you're
of
glad
course.
you don't have tanks to jump into.
Yeah, very much so. Yeah, we fortunately we don't have to deal with that because everything in our system is with a PEM-based system. We're just dealing with the fuel and the air moving through. So we have a membrane that's a little bit more stable and easier to deal with.
So his fuel cell, you put in the hydrogen and you put in the oxygen. Your fuel cell, you just put in the hydrogen?
Yeah, so we'll deal with hydrogen, and Floyd's vehicle had liquid hydrogen. We're dealing with gaseous hydrogen at 700 bar, 10,000 psi, so it's high pressure gas. And then we take the oxygen out of the air because we've been able to develop a compressor system that will move a lot of air through the fuel cell stack, and then through the catalyst, we're able to capture the oxygen and make that get involved in the reaction.
Mm-hmm.
Charlie, General Motors is cooperating, collaborating, doing a joint venture with Honda to develop your fuel cells. We got another question here from the audience. George from Sunnyvale wants to know, did you ever show the Electrovan to Honda engineers?
You know, that's a great question. I don't think they have seen that, and maybe we'll use that at sometime at one of our joint team meetings. Floyd, you'll have to come and talk about it again one more time with the Honda team present there, if that's okay. I think that's a great idea. We should do that.
And George also wants to know, how have you divided the engineering work between GM and Honda to do this joint fuel cell?
So with Honda, it is a one company, one team approach, and that was really critical because
Meaning you've created a standalone company.
well, we've done that now for the manufacturing, but even prior to that, when we were completely two separate companies working on one program, what we decided was you can't have any divisions in the team. If you really want to do this, it's got to be one team. And that's partly, when I was talking with Floyd, it was interesting because he was telling me all the tools he used to keep that one very focused team on the Electrovan working very aggressively and as one team. And we had to do the same thing on the Honda collaboration. So we started out putting all the intellectual property in. GM and Honda had a lot of it, number one and number two in the world in that intellectual property space with fuel cells. So we pulled it all together, cross-licensed to both companies, so we could get access to all the best ideas. And then the teams knew that they would jointly own whatever came out of that development. So we don't have any competition. There was no reason to be competing to get the better part of the project because it's all one team. We put the best resources from either company and they're working side by side. We have people in GM that are Honda engineers. We have GM people that are over at the Honda facility that are GM engineers. And so together we work on this whole thing step by step. When we came to the production side, that's where it made a lot of sense to do the joint venture. And the joint venture, that's a way to make sure that we both own what comes out of that. Again, it's this collective joint shared learning, shared, we both equally benefit from what comes out and we share all the costs and the development that goes with it as well. And so that joint venture will produce the same fuel cell system for both companies.
Floyd, Charlie raises a good point. You had this team, you had 10 months to get the job done. You were pulling them in from all different parts of General Motors. You mentioned Harrison Radiator and Defense Research Labs and the research lab itself. How did you keep that team focused when at the end of it, all you were going to have is a demonstration van?
Well, no one at that time realized the significance of what we were doing. It's only in hindsight after 50 years and a telephone call that we realized that we were doing something that was a historic milestone. Up to that time, I thought this was just history, but we kept the fuel cell team operating not as 200 people all at once. We simply drew in the experts as we needed them at the time that we needed them. And we had absolutely no idea how complex this would turn out to be. We had in effect a blank slate. And when I look back, I can't imagine that one human being could never have imagined what this and made all the decisions. So all of the decisions had to come from the team, from the bottom up, with the brainstorming technique at regular intervals. So once a week we did this.
Floyd, does it surprise you that after 50 years, there aren't more fuel cell vehicles that are available for people to buy?
Well, no, because I was, during my retirement, I had a press pass to the auto show, and I would travel the auto shows, and that's where I would take slide photographs before digital came along and use those to write technical papers. And I, just as a hobby, I followed the development of 11 different vehicles that General Motors built over that 50-year period. So I was kept informed with Google and the press passes. I attended the Frankfurt Motor Show and the one in Switzerland, and I was a regular attendee at the Tokyo Motor Show. So I just simply kept myself up to date by traveling the Asian Pacific Rim into Europe in order to do the homework in order to gather the information to write a technical paper. Once you do your homework for a year, it takes only about 3 or 4 days to put the thing together, because you can pick you've got the resources available, the photographs and whatnot, and you can make a 6-page first draft of a technical paper in just about 3 days. And then I would set it aside and sleep on it, because what happens when you sleep on something, the brain churns away subconsciously. You don't even know it's doing this, and you wake up in the morning and you go back and you keep revising this for a month or two until you get a final draft. Then you mail it in. And then you attend the conference and deliver the lecture. So I did that year by year by year over that entire period from 1988 on to the present.
We've got another comment here from a viewer. Mike from San Francisco says, listening to you reminds him of Lockheed's Skunkworks, where if they had a rough idea, they could develop a prototype in less than a year, and that's almost impossible to do today.
Well, what we did with the Electrovan was just one of a series of projects prior to that and after that. That was our job. That was what we were supposed to do, and we never thought of it as a Skunkworks or impossible at that time. And it's amazing to me that we never were fazed by the next assignment, because after the Electrovan was built, we did a series of 2-passenger urban vehicles, and they were the first piston engine propelled one. Another was a hybrid electric, and another one was an all electric, and another one was a 3-wheeler with a 3rd wheel in front. So those are typical of the projects that we did at the Tech Center. What we were doing what the Tech Centers as a staff function is to evaluate technology to find out if it's ready for commercial production. Then if it was, we would transfer that prototype to a producing division to produce it. And that's the same path that we're following today. It's the same business model that General Motors has.
Charlie, have you learned anything listening to how Floyd and his team did this 50 years ago? Are there lessons to be learned from the past?
Oh, yeah, there are many. I mean, it's interesting because when you're pushing a technology, and there's always doubt, right, when you come into a program, and the way his team over and over again just looked at it and said, well, okay, this is just another set of technical problems, and physics can be used to solve it, and good engineering practice and creativity, and trying to couple many very creative people to do that. I mean, it's very inspiring to hear the story with much less capable tools back then. I mean, computers, other things were not available like what we have today, and yet they would tackle those problems and not be discouraged by how daunting the task really was. That's an amazing motivation when you hit those barriers that just seem overwhelming sometimes in a program. Yeah.
Floyd, what do you think the future is for fuel cells? And I ask it from this standpoint. A lot of people wonder, where are we going to get the hydrogen? And can you make hydrogen in a way that's not going to cause a lot of emissions?
Let's take the last question first, because you've asked several questions there. And here's where we're going to get the hydrogen. It turns out that a reverse fuel cell, PEM fuel cell, is capable of electrolyzing water and converting it into hydrogen and oxygen. So there will be a need for electrolysis of water to produce ultra-pure hydrogen and oxygen. But if we take a look at the installed electrical capacity of the United States currently today, it's operating only at 50% utilization factor. And the remaining 50%, which is unused and which the utility companies would like to use, is equal in generating energy, kilowatt-hour generating capacity to all the gasoline that was sold last year in the United States. So energy, so there's plenty of excess capacity to generate more than enough hydrogen to match the demands of the fuel cell. But in 1900, the piston engine came first, and you got your fuel from a hardware store. And then as soon as the piston engine appeared on the market, gasoline stations began to crop up. So the thing that has to come first is the hydrogen fuel cell entering the marketplace, and the hydrogen is going to follow automatically. We're going to be welcomed by the public utilities because they will be able to use the current installed capacity as we go along.
Mm-hmm. Yeah, that's a really interesting way to think about it, because if you think about a chemical plant, they want to always, refineries are a perfect example. They want to be at the maximum utilization that they can be. That's how they find ways to offset those big investments that come with it. But the utilities are nowhere near that, just like Floyd said, I mean, under 50% utilization. And so having an ability to deal with that, and as well as dealing with the renewables that are being put online, which don't necessarily line supply and demand at the same point in time, you have to have a way to store that energy. And hydrogen is one way to put a lot of energy into storage. It stores electrons for long periods of time and in a very dense way. And that can be one way that the grid can become much more efficient. We don't have to pay people not to turn the wind turbine on. Instead, you can pay somebody else or subsidize somebody else to take the energy when you have nowhere else to put it.
Okay, but tell me this. There's so much advancement being made with battery electric cars. Why fuel cells? Why not battery electrics?
Well, it's a matter of range. Right now, a battery electric car cannot match the range of a fuel cell, hydrogen fuel cell power plant, a vehicle with hydrogen fuel cells. So it's the range that is driving the fuel cell vehicle right now.
Mm-hmm.
So Charlie, just as they did the Electrovan and the Electrovan, General Motors is doing electric vehicles and you guys are developing fuel cell vehicles. Is it a competition, or do you guys share the knowledge the way that they did back then?
Yeah, I don't see them in competition at all. And in fact, I mean, thank goodness, you know, General Motors has a portfolio where we don't have to sit there and look at these technologies as fighting each other. I mean, if you only have one solution, you're stuck, right? But if you can look at it as a portfolio of solutions and you can find places that one solution is better for a certain customer, you can go and target that with that technology. In other places, there might be another better solution. And batteries, a battery electric vehicle is 93% efficient. A fuel cell will never beat that, not in that sense, but it will be constrained by range, like Floyd said. It will be also constrained by time to recharge, and that's a limitation. And putting more and more battery on board to extend that range, that can compromise packaging on the vehicle. That makes the challenge of recharging even harder. So there's a balance there that has to be struck. Fuel cells with the ability to put more energy on in hydrogen can offset that problem. And so that's where the two are very synergistic. And every fuel cell vehicle will usually have a battery, and it's a hybridized vehicle because you want to recapture braking energy. Once you have an electric drive, you don't want to throw that braking energy away. The battery does provide you that benefit. The other thing that you have is you can put, if you think about the economics, you can put a lot of power on board with a battery, but not a lot of energy. So it ends up being a really interesting balance. If you just take the blinders off and say, I'm not just limited to one technology, I'm going to look at how these technologies play together, you can start thinking of energy in terms of hydrogen, power in terms of batteries. It's a very good synergy. And so I'm looking at how the development of the battery happens, and that's good for every fuel cell vehicle out there. We'll get more cost-effective, more dense packaging in batteries, lighter weight batteries, smaller batteries, and scale economies. And that's, in the end, for fuel cells to really push into many more applications cost-effectively, we need scale. And right now, the scale isn't there. So batteries can help that also.
Yeah. Look, we got a lot more to talk about. We have to take another commercial break right now, and we're going to give a shout out to our good friends at Lear who make this show possible.
Lear Connexus offers a parental controls application with geofencing that sends notifications regarding driving behavior and location, including curfew alerts, acceleration alerts, and speed alerts, all delivered to a smartphone application that includes vehicle location, driver notifications, and a report card of driving history, including notifications when predefined geographic boundaries are crossed. For more information, visit Lear.com.
Okay, we're back talking with Floyd and Charlie all about fuel cells. We've got another question here from Steve B., who says, Floyd, are you amazed by how far fuel cell technology has come?
Well, in a sense, I am, because the Chevrolet Colorado ZH2 fuel cell is 1/20th the size of the Electrovan fuel cell system, and it actually is comparable in size to an ordinary piston engine and fits right in the engine compartment. And that was something that was absolutely unthinkable in my day.
That's amazing. So I have to ask you a personal question. How old are you?
92 right now, going on 93.
That's fantastic. Obviously, you stay very active. I mean, are you still doing work on fuel cells?
No, I'm a computer junkie, and spend most of my day on the computer, researching anything that happens to be of interest to me. And when I hear of some new technology, I'm going to do some research on that and put together a PowerPoint presentation of one kind or another as a function of that. And that's the way I keep active during the day.
Okay, do you show anybody these PowerPoint presentations?
Well, I used to use those PowerPoint presentations in my lectures, but my last technical session lecture was in 2013 in San Jose, California. And at that time, what I was interested in was the X Prize 100 mile per gallon equivalent challenge. And what I did was to develop a mathematical model which would enable universities which do not have the kind of test facilities that we have to pre-calculate whether the final estimate the miles per gallon equivalent for this vehicle. And we presented that paper in San Jose. And that was the last one I've done. At the present time, what I'm doing is an occasional, what I call investor professor letter. And that consists of 2 or 3 PowerPoint slides, and I send that out to a limited audience of my relatives and friends.
Floyd, you mentioned that when you developed the Electrovan, that the goal was to drive it by General Motors executives and members of the media. What range did you have Was that it? I mean, it just went around at the tech center and you're
That was
done?
the mission that we had to keep in mind, because that was the function. And it had to be successful because you had the international press and you had a deadline date of October 28th on Friday. And that just had to be the mission that we had to kept our eyeball on, and all else was subordinate to that.
Yeah, it's interesting because after that drive, the vehicle was taken out. They depressurized the tanks, they emptied the tanks, and then it was actually supposed to be scrapped. And no one knows exactly how it didn't get scrapped, but it was hidden away in a warehouse. It turned out we found it in a place in Pontiac, which is about, just miles from where our fuel cell laboratory is today. And someone was able to locate it, and it ended up in the Heritage Center finally. So it was a narrow escape, but it almost got scrapped.
But it literally just drove a mile, maybe?
It's probably just over a mile if you go all the way around the tech center.
Right.
Yeah, that's all it drove. And actually, Floyd had never been seated in that vehicle until we brought him back for the anniversary. So I had to make it up for him. I had him sit in the ZH2 before I ever sat in it, because we had to make up for him never riding in that vehicle.
Yeah, the first time I learned that the fuel cell, the Electrovan, still existed was when Craig Marks, who was the executive director at that time, called me in 2006 and said, "Floyd, do you know that the Electrovan is still in existence? Because we're putting together a public relations press release for the New York Times." So that was the first time we heard of it, and both of us were amazed that they had still existed, because we thought it had been scrapped.
Yeah. I actually knew Craig Marks fairly well. I mean, he was, our careers overlapped a bit. But Armand wants to know, another viewer, the Electrovan is still around. He wants to know if he can go see it.
Yeah, so the Electrovan right now, it's housed in the GM Heritage Center, which is over in Warren. It's not too far from the tech center.
But that's not open to the public.
Certain times it is.
Oh, really?
Sometimes through SAE, there's certain events.
Okay.
Usually it's not a normal public museum, but we do take it out to different places periodically to get it out in public, and there are a couple opportunities we think might be coming up in the next year and a half. So
But it's not drivable, is it?
It's not drivable, no. But it's, we'll never drive that vehicle again. But it looks just like the day it was taken out of service. So just stay tuned. I think there will be some times. It actually was in the Peterson Museum for a while out in California. And so we'll see, maybe in a year and a half, we'll probably get it out where you can get another opportunity to see it.
So I read that there's 550 feet of pipe in that vehicle.
Well, I don't know how many feet of pipe, but I'll bet there are miles and miles of electrical wiring, because what we did was build into the vehicle. If you remove all of the trim panels, you'll find the sides of the vehicle and the interior floor covered with electrical wiring, in which there were automatic safety fixes and alarms. And the only person who ever drove that vehicle was Dan Frank. He was the hands-on guy that knew how to start it in the fuel cell development laboratory, and he was the driver and the only person that ever drove it, because there were 30 fault lights on the instrument panel, besides all of the automatic fixes that were built into the system, all safety, and he knew what those would say. So I never drove it, Craig Marks never drove it, Ed Cole never drove it, because that would be a first for him, because the first thing he ever drove when we had an experimental car was that car. And he would floorboard it around the test track that we had at the tech center. And he did that to the first Electrovan that we had. And what happened at that time was, with the silver zinc batteries, they were also potassium hydroxide electrolyte type of a battery. And he floorboarded until the electrolyte began to boil and exploded. So we lost $100,000 worth of silver zinc batteries in that 1964. So that's why we built the second one, because we then realized we had to air cool the batteries, separate them so we could pump air through them, and air cool the traction motor with by actually circulating cooling oil through that traction motor. So that's the system that was developed to transfer it into the van. So we had to do those in two separate steps. We couldn't have possibly done the drive system and the fuel cells at the same time. But that gave Union Carbide 3 years to develop a simplified practical version of the fuel cell based on the spinoff from the Saturn Apollo program.
It took you quite a while to start the fuel cell, didn't it?
Well, our best startup time was 3 hours. Because we went through a countdown procedure. The first thing we had to do was have an auxiliary power system of lead-acid batteries to get the blowers and the pumps and all of the electronics working. That was external. It was like starting an airplane with a auxiliary APU, auxiliary power unit. Then the next thing we would do is pressurize the system with argon to check it for leaks, because there was so much plumbing, as you had already mentioned. Then the next thing we did was introduce oxygen on the oxygen side. Then we would load the potassium hydroxide electrolyte. Then they would load the hydrogen on the hydrogen side. And once the fuel cell systems began to function, we would disconnect the lead-acid batteries, and the system would be operating at idle at that time. So the countdown procedure was like launching a Saturn into space. That took us 3 hours. The first time we did it, it took us 3 weeks.
Wow.
Because
So how long-
we were learning, we didn't know what this procedure was except by trial and error. Everything was a blank slate. We had to learn as we went along.
And the fueling was done in a bunker, wasn't it? They actually had the tanks fueled in a bunker when they were pressurized?
Well, one of the things we did at that time was for everything that we did, we had backup alternatives, because we couldn't do anything in series. So we bought cylindrical 8,000 PSI tanks that were man-rated and part of the Apollo program from Walter Kitty. And since I was terrified at the idea of 8,000 PSI, because 2,000 PSI in a acetylene or an oxygen tank in the lab was everyday item. So we built a ASME qualified bunker in the southeast corner of the tech center across from the engineering staff building. And we had a plexiglass window looking out to the outside with a canvas top to protect the tanks outside. And we began to pump them up 1,000 PSI at a time. 1,000 PSI the first day, 1,000 PSI the second day. And what happened on the second day is we had a pneumatic rupture of the first tank. It was qualified by Walter Kitty for 8,000 PSI. So that ended that option, because this was in September and was only 2 months away from the 28th. And so we opted for the cryogenic liquid hydrogen and oxygen tanks, and that's how we drove by the press show, international press show.
Amazing.
We just said there's no time to get a new set of tanks from Walter Kitty and for them to find out why this failed. And what we did indirectly, obviously, was somehow save perhaps the Saturn Apollo program, because that was part of tanks that were used on board, destined to be used on board future flights.
Wow.
Now, Apollo 13 actually ruptured a spherical oxygen tank, but that again was a pneumatic rupture. And the reason it ruptured is because liquid oxygen is very cold. It's way below freezing. It's a sub-temperature item. And when you reduce the temperature of steel below a critical point, it changes from ductile fracture to brittle fracture. And brittle fracture is a grenade-like pneumatic rupture, which proceeds at the velocity of sound in the steel. So that's a lesson that we learned from that experiment.
Mm-hmm. And how did you reconstruct that failure? You had, didn't you?
Yeah, we simply didn't bother to use it. We just set it aside.
Okay.
So did it make any difference? So when you developed the fuel cell system initially, you thought you would have gaseous hydrogen, but then you used liquid hydrogen. Was there any difference?
At that time, we were aware of wire-bound oxygen tanks that were used during World War II. And then I think it was Sundstrand had developed plastic fiberglass tanks. So we went out to look at those. We flew out to Sundstrand to look those over as a possible option. That was after this, but they were still under development at that time, so we abandoned that idea and simply fell back on the backup option, which was liquid.
Very good. With that, we're going to have to wrap up this show, but Floyd Wyczalek, thanks so much for coming on Autoline After Hours. It's been a real pleasure having you here.
Well, it's been an honor and an opportunity that I would never have imagined, and I still don't believe this is real.
Charlie Freese, great having you on board
Thanks
here today,
for
too. Yeah.
I'm glad I could be here with Floyd and you.
Yeah,
Thanks.
great.
This is a historic show.
It is a historic show. So, Gary, good seeing you. We'll do it again next week.
We will.
Want to invite all of you back there to the studio next week as well. And thanks for watching Autoline After Hours.
Autoline After Hours is brought to you by Bridgestone Tires, your journey, our passion, and by Lear, a global leader in automotive seating and electrical systems.
Visit our website, Autoline.tv, where you can watch us live Thursday afternoons. Get your daily fix with Autoline Daily and in-depth analysis and interviews with Autoline This Week. There's all that and much more at Autoline.tv.
When they were doing this startup procedure and they had to have the APU unit to get the fuel cell going, but now it's just like starting a car with gasoline?
Yeah, I mean, basically now, and we don't even, in some cases, we don't even have a key. You have a button, right? And you have power almost instantaneously. There's a little warm up. I mean, you won't be at full power just right off the bat, but by the time you pull out of the garage, you're basically able to do anything that you'd expect to do with the vehicle. And so it comes up very quickly. And even the refueling, I mean, Floyd was talking about the weeks to refuel. We were basically able to go out and get a less than 3-minute refill on any vehicle that we do now, right from empty.
John and I drove the Clarity, and we had the opportunity to refuel that at a commercial station in California. I mean, it was just like pumping gas.
Yeah, it's very transparent, but it's so funny because the things that Floyd talked about, the safety measures, and when you don't know what the technology is like, you're very conservative. And then as the science evolves and we prove things and we get better models and things, you can start backing away from that. I can remember the first Equinoxes, we had to basically ground the vehicle with a grounding line every time you had to refuel. Things like that were all these safety measures. And then over time, we got experience on what was required and how safe the technology could really be. Mm-hmm. And even the tanks, they're now carbon fiber wrapped tanks, so they can hold that 10,000 psi of hydrogen, but it's done in a very, very robust way. And if you think about it, you actually have very little chemical energy. So on board, you might have 5 kilograms of hydrogen, which is the chemical energy of about 5 gallons of gasoline. So you put 5 gallons of gasoline in the back of your car for your lawnmower, and you don't think twice about it. So the other part is the pressure. And the pressure, we have carbon fiber wrapping that makes these tanks actually stronger when they're under pressure. So one of the tests we use is we actually fire rifles at the 50 caliber rifles, and they won't penetrate the tank.
That's amazing.
You know, we wanted for the last fall, we had the Colorado ZH2 at a show, and we wanted to have examples of the different parts. So we had the tanks out, and we actually we actually removed a piece about that big out of the tank, and we went through 38 Sawzall blades, cutting that little piece out of the tank. So they're very, very strong, but it took all the work that came right back to the work Floyd had done to start that process along. Yeah. It's pretty
Isn't a truck better suited for fuel cells just from packaging the tank?
Well, it certainly, I mean, anytime you're packaging constrained, a bigger vehicle can help you with that. I guess we're now down where we can do it in a smaller car. I mean, there are plenty of examples. You saw the Honda vehicle. They've done a very nice job packaging a lot of hydrogen on board. But I think we have to look at where the incentive is for the customer and how we strike the right balance. And certainly a larger vehicle will be more challenged to get a BEV type solution and still keep the range and the utility. So even whether there's a compromise on the tank or not, you can actually have a customer incentive why the hydrogen fuel cell can give you that zero emission, very capable high torque range, you know, all these other things that come along with the fuel cell, and that can be a good thing. And then you can also get some of the other interesting things that are coming out of the work we're doing now with the Colorado. The Army's interested, of course, in things like quiet, you know, stealthy, low thermal signature, all those things, and they come for free with a hydrogen fuel cell. So we were testing that ZH2 out in Milford, and we had people out trying to take pictures of it, going through, you know, blasting through puddles and things. So they post up on the hill, and they were waiting and trying to get the vehicle when it came into view, and they couldn't hear it. They started having to time when it hit the last puddle, how long it would take to get into the field of view, and then start taking pictures and things like that. So, you know, that all is really nice incentive, and that comes along just by virtue of having a fuel cell. You make water too, which if you're in a certain a desert environment, having water there is a good thing, and so a lot of advantages that come out of it.
Yeah.
But I mean, if you're out in the middle of a desert somewhere, I mean, isn't it easier to have barrels full of liquid normal fuel than trying to bring in tanks of, I mean, whatever you'd bring in, I don't even know.
Well, that's a great observation, and at first blush, you would say, wow, you know, the Army brings JP8 jet fuel, and they bring it from the United States refineries to wherever they need it, and that's a long supply chain. And so you'd think that, well, okay, if I've done all the work and I've got to get it there, then I want to just use that. But it turns out you can actually go through a reforming process to make the hydrogen even from JP8. And even though you give up some of the energy when you go through that reforming process, because the fuel cell is more efficient than many of the other propulsion system alternatives, you can get more miles on the hydrogen that comes off the backside of that reformation. So that's one thing you can do. But they're also looking at ways that how can they, I mean, hydrogen is an energy translator. That's all it is. It's a way to store a lot of electrons, and you can go into or out of hydrogen. So what we can start to do is you can start to think about using whatever fuels are available in theater for the military. So if they've got you know, other types of petroleum-based fuels, they can use those. If they have a grid, they can take energy off the grid, and like Floyd was describing, you could go in and use it's basically a fuel cell in reverse electrolysis. You can make the hydrogen with that grid energy, or you can use renewables. It can be wind or solar or whatever is available. You can use that as your source of fuel. So I don't see hydrogen just immediately solving all the same applications that right now JP8 is doing, but it can be a way to offset certain applications and get capability that maybe isn't available with more conventional propulsion systems today.
I've seen some stuff online of new ways of making hydrogen, very low energy needed. Are you following these sort of things? Does any of this make, and it's all in the labs, nothing's commercialized.
Yeah, there's a lot of work going on. There's some work going on in some of the labs where they're trying to simulate. It's kind of like simulated photosynthesis, basically. Basically, if you have a way to take the solar energy and then capture it and then effectively convert it to hydrogen and do it cost effectively, that could be very interesting. So there are a lot of people that are working on ways to do that and do it without a lot of the precious metals and things that are otherwise required. So that's interesting. We'll see how it develops. Right now, the most cost-effective ways to get it in bulk are to use it either from steam methane reforming, which is done quite often today, or using these ways to augment the grid by using the renewables and converting those to hydrogen as that way to buffer energy. Those are some of the most interesting ways up front in the nearer term. And then hopefully some of these other things might develop over time. It could get really interesting.
Can you use waste gas like methane?
Yes, and methane is a great source. Actually, there was one experiment that has been demonstrated now in California where they were using waste sewage treatment gases that were being off-gassed from the treatment of sewage gases, and you could capture that. You can also do it with landfills, and you can relatively easily convert that into both power directly or hydrogen. You can actually think about doing it in stages. There was actually a molten carbonate bank of fuel cells. That's a different fuel cell technology than what we're using. But what they do is they could capture that methane, make power, and then they have a waste gas stream that they can break off, which is hydrogen. So now you can take something that becomes kind of a base load plant, and you can use that hydrogen, and we could put maybe PEM-based fuel cells on the back end, and we become a peaker. Now, that's much more valuable than having a base load that's trying to compete with nuclear energy. Instead, you're trying to do the peaking and following, which is very valuable. And that's another way to do it. And then you can further take that system and capture the heat energy and do kind of a combined heat and power type thing. And you can heat buildings, you can use it for industrial processes, all sorts of things. So once you start to, the real advantage on hydrogen and fuel cells is when you really start cutting outside of swim lanes. You know, as long as you just focus on one little thing, it's hard in the startup phase. But if you start thinking broadly, there are many ways that you can solve multiple problems with the same technological solution.
So you guys are thinking about things that go beyond cars.
Absolutely, yeah. We're working right now. So a fuel cell, we can use the same parts just by stacking them up. And if you need more power, you put more cells. If you need less power, you use fewer cells. And that's a big advantage because by the same investment in a manufacturing plant, you can have low power systems, high power systems. You can apply them to a range of applications. So one of the things we've been talking about lately has been the work we've been doing in these unmanned undersea vehicles. And that gets really interesting because Floyd mentioned range, right? And the ability to put a lot of energy on board, and the fact that the Electrovan couldn't get enough range with batteries, and the fuel cell with hydrogen was the solution to try to get more range. Well, similarly today, batteries have evolved dramatically, fuel cells have evolved dramatically, but there's still a difference between the ability to put a lot of energy on board. So if you put batteries into one of these unmanned undersea vehicles, you're talking about hours to days of mission. If you put hydrogen and fuel cells in, you're talking about months. and that makes a big difference. So with that technology, we've been working with the Office of Naval Research and the Naval Research Laboratory to do work on that. And we've got over 1,000 hours in the water with a system like that, and it's using the same technology again. So we don't need to go and invest in a brand new propulsion system that's all different from everything we've done before. We can take that same technology and transfer it over. There's some other things you can start to think about. You can talk about aerospace. And aerospace, I think, is very interesting. It's hard to break into that market because, I mean, certainly it's got to be, you've got to kind of earn your way in, and the vehicles don't go through 4-year cycles like we do in automotive. I mean, they're 40-year cycles, right? So you got to find that sweet spot. But imagine in commercial aircraft where right now you have something called a ram air turbine. And this is a system that's used like when the plane landed on the Hudson River because both engines were lost. This is how you get the power to propel or control the control surfaces on the airplane when you're in one of those very desperate crash situations. So what they do is they push this ram air turbine out of the fuselage or the hull of the plane, and it's basically a propeller, and it's acting like a windmill, and it makes the power during that last ditch scenario. Well, that's something that you never want to use. So you're carrying it for the life of the plane with no value unless you're ever in one of those really unfortunate situations. A fuel cell can be a really interesting alternative. So a fuel cell could be your backup power on the aircraft. And when you're in a situation like that, you divert that energy to control all of the hydraulic pumps and the actuators on the wings and the control surfaces. And now you've got a way to do that, but while you're not in one of those desperate situations, you can use it to heat coffee on the coffee pots or whatever else, right? It gets very interesting. But then you can start thinking even further. So what would be the next step? Think of it as a replacement to the fire suppression system in the cargo hold. So right now they use a halon fire extinguishing system. Halon is something that won't be produced or used in the future, so what's the best alternative? Well, one of the candidates is oxygen-depleted humidified air. So that's fuel cell exhaust. You know, we take air, you take out the oxygen, use it to make electric power, and what do you put out the back end? Basically a nitrogen-rich gas with basically no oxygen in it, and water, it's humidified. So that becomes the fire suppression system. So the very same system that you hope you never use for backup power could ultimately be your fire suppression system, and those get used multiple times every year. I mean, you know, batteries in the cargo hold that don't behave themselves. I mean, some way you've got to be able to put those fires out. You know, I don't like thinking about it either. But actually, the more I learn about this, you got to put these things aside when you get in the aircraft. But it's a really interesting thing, because then you can start thinking about even other things, right? So once you put the system on board, then the next thing is, how do you inert the tanks over the fuel over the wings? Well, if you just don't humidify what you're putting out the back end, if you separate that water, then you can use the nitrogen as the inerting system. And they're using tanks of nitrogen as the inerting agent in those wings. So you can overcome that as well. And then you can start to say, okay, well, now if I've got an FAA certified system and it can do all those things, what else can you do with it? Well, if you're making even a fuel cell system as small as what we have in, like, for instance, the Equinox or the ZH2, that's 2 gallons of water an hour. So now you can start thinking of that as a way to flush toilets or humidify the cabin, or you can do all these different things. And that's using, again, the same mass, the same system. You can do multiple functions that are required on the aircraft with one system that can do all these different things. And then you can start thinking, okay, well, now if you've got that, why not turn it on when you're loading bags into the cargo hold? So if you just take that noisy turbine out of the back, that turbines don't really like running at ground level. It works much better in the air. And instead, you have a quiet fuel cell system that's zero emissions, and it's doing this very efficiently. You won't have all those guys with, the ear protection trying to load the bags onto and off of the aircraft, and you can do that more efficiently as well. So now the creature comforts of the air conditioning and everything else can be supported on the ground more efficiently without the emissions and the other things that go with that. And then you can go even further, right? So now think about.
I think Alan Mulally went to work for the wrong company.
Well, just think about what happens right now. You have you mentioned it with the Electrovan. Miles of tubes and miles of wire. Well, they got rid of miles of hydraulic tubes because they decentralized the hydraulic pumps on the commercial aircraft. And instead, they went to smaller hydraulic pumps that are distributed around the plane. But you have to get the electricity to those pumps. And so now there still are miles of wire. So now what would it be like if you, instead of having one power generation system and all connected with miles of wire, you could use smaller fuel cell systems distributed up and down the aircraft, and you could deal with it that way. So now you can correct another challenge, right?
And you've got redundancy.
And you've got redundancy. So a lot of opportunity. I mean, it's a different paradigm, and you got to get in the right place and start developing these things. But they could be a really interesting way to change that business. And then how does that relate to us? I mean, then we can start to say, well, okay, they will see the same challenges that we see in terms of hydrogen and infrastructure, right? So you have to be able to supply it at the place where the planes are refueling. But they refuel, they take off and land in a predictable way from airports. So put the infrastructure in at the airports, and you know how much you'll need. You can optimize that system. You don't have to have a station where you're not sure how many people will fuel that day. You know how many planes will be coming in, how many will be going out. You can optimize that infrastructure so it's tuned for the right load. And that does another thing for you. So around every one of those aircraft are things like ground support vehicles. And they're using, they're not that much different than something like a forklift, which a lot of forklifts today are going to fuel cells because you don't have to have batteries that you replace. You don't have to have petroleum-based fuels. I mean, all of those things, you can think about replacing those also with fuel cells and using the same infrastructure that you use for the aircraft for the ground support equipment. And then I get really interested from the automotive side, because the other thing that comes into the airport are a lot of vehicles, right? Rental fleets. And so those rental fleets are all centrally located very close to the airports. And I don't know about you guys, but I can't remember the last rental car I had where I fueled it more than just to return it to the airport. Now, I know a lot of people have other needs, but a large proportion of the rental fleets are only used where they're just refueling to come back. You don't use the full tank. So that could be a source of hydrogen for those fleets, and then you have an efficient zero-emission solution for those fleets as well. So there's a lot of things where if you just, again, get out of the swim lane and start thinking broadly, this technology can really cut across a lot of those things. And the Department of Energy is doing a lot of that work right now. They have a project called Hydrogen at Scale. You talked to Brian Pivovar a while ago on that. And it's trying to explore some of those opportunities where you can start to bring the cost down, you can bring the utilization up, and you can start thinking of hydrogen the way the chemical industries and others do, as a way of optimizing the system, bringing the cost down, and using it to cut across those boundaries. It's really an interesting opportunity.
Wow.
I want to go back to the landfills
Yes.
for a moment. Is there enough methane coming out of landfills that they could be a significant source of fuel?
Yeah, actually, we're taking a lot of the captured methane out of a landfill that's up by our Orion plant, and we're using that to produce power. And so, yes, you can do a lot of that. It's not trivial. It's something you have to take very seriously. And the sewage treatment plants, it's the same thing. Actually, you know, it's even more than just is there enough. These are actually greenhouse gases that are being vented in some cases, and even hydrogen in some cases is vented as a waste product. The perchloroalkali plants, sometimes you don't have a ready-made place to send that hydrogen where it makes sense to capture it. And part of the cost of hydrogen isn't just the production, it's the distribution. So if you don't have a pipeline and you haven't invested in one, then it's a tube trailer truck. And that's a fairly high cost way of shipping the hydrogen. So if you think about it, if you capture that energy, and that's where this reverse fuel cell, the electrolyzer, becomes so interesting, because now you can start thinking about using electrical grid to move the hydrogen in the form of electrons on the grid and take it back off through electrolysis where you want to use it in vehicles or stationary power or aircraft or whatever it happens to be. So it gets really interesting to kind of explore a model like that. Yeah, and then you can also think about things like within a plant, right? Like the forklifts, because one of the places that the fuel cell's taking off, and I gotta admit, I'm surprised at how that's been gaining a foothold as fast as it has. But a battery in a forklift, which is kind of the normal technology in a lot of these cases, a battery is going to have, usually you'll have a forklift, you'll have 1 or 2 extra batteries for that forklift that are in a big battery room, and they're charging while the forklift is on shift. And if you run a 3-shift operation, a company like Walmart does that, and you have things like food storage in cold freezers, things like that, they don't want to have emissions because you're dealing with food, and they want to keep that vehicle constantly running. So if you don't have to go off and do a battery transfer, take one out, put another one in, that's a good thing. If you don't have to go out and deal with the fact that the battery, when it gets cold, and it loses its charge, the performance of the forklift declines. Instead, you go to hydrogen and you just, in a couple of minutes, fully refuel it. You have no extra battery. You can take all that floor space out of the plant for a battery room. That's all good. So there's a lot of things like that you can do. That there's just no other solution. And now think about things like delivery vehicles like FedEx, UPS, these others. Now you can start saying, well, if you have this ability to put these vehicles out there that way, now you can start to deal with the fact that some cities are trying to ban carbon-emitting vehicles. And some vehicles, they're trying to get in there and do deliveries at night because of traffic during the daytime. Well, the last thing you want are noisy vehicles doing that. Well, the same thing I told you about a quiet fuel cell, that's an advantage, because now you can start to think about these vehicles that can quietly go in and do that work and be relatively, not disturb the people that are living there day and night. A lot of other interesting things. As you start talking about cities, you know, the population of the cities has gotten larger and larger, and the problem is they were set up with infrastructure that's aging. It didn't anticipate a lot of computers. It didn't anticipate big flat screen TVs that consume a lot of power, and so, or air conditioners in many cases. So what happens is the city electrical demand has gone up and up, but the pipeline to get the electrons in and out of the city hasn't necessarily kept pace. And so the way that they've tried to adapt to that is spinning reserves, so natural gas-fired turbines that, you know, they'll do that peaking. But that's actually something a lot of municipalities are pushing back against. They want to get rid of those spinning reserves. So then you have a new challenge, which is how do you deal with that? Well, the interesting thing is you could use the nighttime to bank your electrons in the form of hydrogen, go through the electrolysis, right? Store your hydrogen. You could think of doing it on the tops of the buildings. And then that becomes your peaker during the day if you reverse the process, but it also becomes your emergency backup power system, which almost all of these facilities have to have anyway. When Hurricane Sandy hit, the only places that were running were places that had a very good backup system. It could have been a diesel system. Some of them have fuel cell systems, and so you can provide that free of charge just for having this ability to do this peaking and offset that other demand on the grid. So a lot of things like that we're trying to explore and find ways to bring this overall system more optimal.
Yeah, very
Fascinating.
Yeah, it is fascinating. Well, look, we should clear the studio so the crew can get its work done and set you guys on your way.
Well, thanks for having us.
Oh, this has been great. This is fun. Very fun.